Hello, welcome to another episode of Chemistry. Today we're going to talk about galvanic cells. Specifically, what I want to talk to you about is what it looks like, the design of it, then seeing if we can pick out or predict the oxidation reduction reactions happening in each of the half cells of galvanic cells, and also trying to figure out how to calculate the voltage of the cell. Okay, so what's the overall function of a galvanic cell? Is it takes chemical energy and it converts that into electrical energy. So your battery, as an example. So there's chemical energy within the batteries, and then some process happens in there, and then it turns it into electrical energy that you can use for your whatever products you want to use. And it does this via spontaneous redox reactions. So what does the basic structure look like? Now, this is a very basic one. Guaranteed the ones that you see in your exams are going to look completely different. This is way too easy. But anyway, let's go through them. So you can see here there are two what we call half cells, right? And you can imagine if it's a redox reaction, in one half cell there's going to be oxidation, in the other half cell there's going to be reduction. Cool. So let's look at each individual cell because it's pretty much replicated across both. You'll have what we call electrodes. So usually some sort of solid component here dipped in some sort of solution that we call an electrolyte. Now, the purpose of that solid is to allow for the flow of electrons, right? So it has to be able to conduct electricity. Then these two electrodes are connected by a wire. Now, this is an external wire here. And what happens is if it's going to be electrical energy, the electrons are going to be moving through this wire. Now, depending on where the oxidation and reduction half reactions are, it'll tell you the direction in which the electrons are moving. As I mentioned before, within these, you'll normally have an electrolyte, and that just means that there's a solution with ions floating around in it. The last thing is, if you think about what's happening so far, if we didn't have this last component, we actually wouldn't have a complete circuit. So the last part of it is we have a salt bridge. And as I mentioned, the salt bridge connects the two half cells. It kind of completes the circuit, but it has some really other important functions as well that we're going to go through. Okay, so this is the very basic structure. Two half cells. Within each half cell, there's an electrode stuck in there. So there's some liquid, the electrolyte, and these two half cells are connected externally by a wire. That's where the electrons can actually flow through, and also through a salt bridge where the ions move through. So that was a lot to talk about. Let's summarize that. As I mentioned, two half cells. Oxidation happens in one, reduction happens in the other. We can't have redox without those two. One of those is going to be what we call an anode, which will be a negative polarity. Now, anode is where oxidation occurs. So remember, an ox. The cathode is where reduction occurs, like a cat, right? And it's positive in terms of its polarity, it's positive. So anode, oxidation, cathode, reduction, a red cat. I try to get a red cat, but see the red eyes, I don't know. And the salt bridge there allows for the ions to flow through. And what it does is not only does it complete the circuit, but it does what's called, it maintains what we call electrical neutrality. So there's no buildup of charge in either side because the ions are going to move to these half cells and neutralize it as much as possible. We just have to make sure that when we have a salt bridge, whatever you pick doesn't interfere with the actual reaction in the half cells. Otherwise, you're going to screw up what's happening. You're going to screw up the redox reactions that are happening in this galvanic cell. How does it work? So here's an example. Now, we know that at the anode, that's where oxidation happens. So an ox. What is oxidation? We know that oxidation is the loss of electrons. Great. So at this electrode here, you're losing electrons. You can see that you'll lose the electrons from this electrode, and that will then cause the electrons to move outside the wire in that direction. So from the anode over to the cathode. Remember, the cathode is where reduction occurs. Now, reduction, we're talking about gain of electrons. So at this point here, the electrons are moving from the anode over to the cathode. So from the point at which they are lost to the point at which they are gained on the other side here. In this reaction, you can see that the copper ions here are gaining the two electrons that are coming from the wire down the electrode to form copper solid. On the flip side, what's happening is zinc here is being oxidized into zinc ion and electrons. So you can see here zinc solid jumping into solution in the process, losing electrons that are moving up the electrode through the wire. And that's why I said it was important in terms of the electrode. They have to be able to conduct electricity. So they have to allow for these electrons to actually flow through. Otherwise, it's not going to work. So that's kind of the basic operation. The other bits is that this salt bridge, now the purpose of the salt bridge, as we said, is to maintain electrical neutrality. What you'll notice starting to happen is over in the anode, over in this half cell here where oxidation is occurring, more and more zinc ions are being sent into the solution, into the electrolyte. What does that mean? The buildup of that positive charge means that that half cell starts to become really, really positive now. So to combat that, what's going to happen is the ions, specifically the anions that are in the salt bridge, are going to go over to this side and go, sweet, you're really positive, I'm really negative, I'm going to come over and neutralize you as much as I can, right? So the anions will migrate to the anode. On the flip side, you can see the reverse being true. Now, these copper 2 plus ions are actually then being taken away from the solution. What we don't see here is there's probably some sort of negative ion here. So let's say, for example, there's sulfate ions. Now, as you're losing that positive charge out of the solution, out of the electrolyte, what's remaining is, yes, the negative anion that was originally as part of that solution. And so what happens then is that the cations in the salt bridge, they start to move over to this side of the galvanic cell. And the purpose, again, same thing. There's starting to be a buildup of negative charge in the electrolyte. So we chuck in some cations to neutralize that out. So here we can remember that the cations will actually, the cations will migrate towards the cathode. So that's generally how it works. And you can see up here, which is something that we'll calculate soon, is that you can even calculate how much electrical energy, theoretically, will be produced as a result of this galvanic cell and these two half reactions occurring. The salt bridge. I've talked about it a little bit, but let's just summarize it in words. As the reaction proceeds, what's going to happen is there's going to be a buildup of 2 plus ions in one half cell. In the other, there's going to be an imbalance of charge because that is being reduced, so you're losing that as part from the electrolyte. Therefore, what's going to happen is the anions and cations will flow to the anode and the cathode respectively to make sure those charges remain constant. So anions to the anode, cations to the cathode, just to restore that balance in charge. Reactions in a galvanic cell, how do you pick them out? Time to use the electrochemical series. As I said, redox electrochemical series, you really have to know how to read that. And by doing that, you can figure out any redox reactions that are occurring in any cell. This needs to be your bestie when it comes to your exam. Let's look at this as an example. So I've been giving you a cell here. This is beautiful, coming from the Queensland QC chemistry exam. And you can see you've got copper electrodes here, you've got zinc electrode here, you've got zinc ions, and you've got copper ions here, as well as the nitrate and the nitrates. The salt bridge, you have potassium nitrate. Now, you know that potassium nitrate actually consists of potassium and nitrate ions, and this might be important in case there's some sort of question around movement of ions in the salt bridge. Cool. Now, let's see how we can actually figure out the reactions that are occurring in this galvanic cell. What I need you to do is everything that you can see that's present in the galvanic cell, you go and you circle and you find in the electrochemical series. So let's start from the left-hand side. We've got copper electrode, which is copper solid. We've got copper 2 plus ions. We've got nitrate ions. Something that you also need to consider is when you're making a solution, in order to make it a solution, most of the time the solvent we're using is actually water. So what's actually involved here is water also. And a lot of teachers won't teach it this way, but I will. And the reason for this is in the more than 10 years of experience that I've had teaching this, what will generally happen is your teachers will teach you one thing for galvanic cells, but as soon as we head over to electrolytic cells, you have to consider water and things feel like they change, but it's not true. So I want to teach you the fundamentals of redox and the electrochemical series from the very start, so it doesn't feel like you're learning something new when you go to a different type of cell, because fundamentally redox is the same. So we'll go over to here and I'm just going to circle all the stuff that I find. So I've got copper solid, I've got lots of water, circle all the waters, just get used to doing this stuff. No nitrate ions. By the way, you won't find them. Same as you wouldn't find sulfate ions on your electrochemical series. Cool, so that's everything I've got on that side. On the other side, I'm just going to change the color. I said I've got the copper 2 plus ions. Cool. So let's circle this guy and any waters that I can find. Cool, so that's for the half cell on the left-hand side. And now let's look at the half cell on the right-hand side. So I've got zinc. We're going to do the same. Zinc, nitrate. Of course, water's in there if I make a solution, as well as zinc electrode. I've got in both of the half cells that is present. I don't circle the stuff that's in the salt bridge, by the way, only in the half cells. And then I think to myself, what's the strongest oxidant and the strongest reductant in what I've circled? Now you see that I've strategically used two different colors so that we can see. Everything on the left-hand side is oxidants. Everything on the right-hand side is reductants or reducing agents. So I'm going to find my strongest oxidant. According to what I've circled, it looks like it's water. If that is true, and the reaction needs to proceed from left to right, where the water is gaining the 4 electrons, we also need the presence of oxygen, additional oxygen, not just the oxygen that's available in the air. And because I don't have this, I can't consider this as part of this mix. So it's not my strongest oxidant. So I go to my next strongest one, which is copper 2+. So I can see here that that's my strongest oxidant. Going on the right-hand side, my strongest reductant is this side. Now, if you have a look at the E0 values, you can see that the E0 value for the strongest oxidant is higher than the E0 value from the strongest reductant. That means a spontaneous reaction will occur, which is why galvanic cells can work. So what that means is the reaction at the top, my strongest oxidant is going to go from left to right, so the copper 2+ ions will gain 2 electrons, whereas on the flip side, my zinc solid, will undergo oxidation to form zinc 2+ ions. So if I was to write it right underneath the half cell, just to make life easier for us, the reactions would look like this. Cool? So these are my two half reactions. Copper 2+ ions undergoing reduction, zinc solid undergoing oxidation. Now with that, we can start to actually label our galvanic cell as well. So if this is the case, then this is the site of reduction, right? So this guy here is our cathode. That's the site of reduction. That's positive in terms of polarity. Over here, the zinc is actually our anode, because I know that oxidation is occurring here, negative polarity. So these are the half reactions that are occurring in each of these cells, and you can start to label them, which is really great. What we'll also know is that the electrons will flow from where we lose them to where we gain them. So just showing you how this all works. So the electrons will be going in that direction. Cool. So let's start to think about what moves through the salt bridge, if that's the case. Now, from the previous question, we've been able to identify that this is my cathode, this is my anode. And here, the zinc solid is being oxidized, and that my copper ions are being reduced. So what that means is over time, a lot of the copper ions are going over to here, which means that I'm going to get a buildup of whatever's left over, and that is the nitrate ions. So considering that this is potassium ions as well as nitrate ions, we're looking for the cations, so the positively charged ions, to move over to this cell here on the left-hand side, because I'm fearing that there's going to be an overwhelming negative charge in that half cell. So you can see that here, the potassium ions will go here, which means that my nitrate ions will go in this direction. Cool? And that's going to balance out all of the charges of the zinc 2+ ions. That's going to drop into the solution like that and become more and more positive. So what if you wanted to calculate how much electrical energy you get from the cell? The only thing you really need to do is you have to think about, it's just the difference between the E0 values of the reduction reaction and the oxidation reaction. That's it. So if you have a look at this example that we had before, of the two, reactions that are occurring, my strongest oxidant was that, my strongest reductant was that. So it's the difference between these two values. That's it. Cool. You can calculate it however you want to. You could probably already see it, but what we can do here, E0 value, 0.34 minus, see it's a minus number, 0.76. Total of that is 1.1 volts. Cool. So let's summarize what we went through. Galvanic cells are really good at converting chemical to electrical energy. Remember, anode, cathode, the solid things in each of those half cells. You've got an electrolyte, both of those beakers, electrolyte in there. You've got an external wire where the electrons move through, and you've got a salt bridge to connect the two again and to also maintain that electrical neutrality. All of these play a really important role in how a galvanic cell operates. If you ever want to calculate the electrical energy that's generated, all you need to do is to figure out the difference between the reduction reaction and the oxidation reaction. So this is a way that you can do that. Just know that that's the maximum amount of electrical energy that can be generated. It's not necessarily always the case that it's going to happen, especially in an experiment that you do in class, different conditions. All right, cool. Thank you so much for hanging out with me today. Hopefully you learned something new or more or consolidated about galvanic cells. Always remember, no matter what anybody says, yeah, you can.